You think you've wrapped your head around gravity? Step on a scale. Look at the number. That's your weight. Earth tugging on you. Simple. Drop a pen. It drops. The moon loops around Earth. Planets revolve around the sun. Mass attracts mass. Newton solved it ages ago. Gravity, an obvious everyday force. Easy, clear, except wrong. Not slightly wrong, profoundly wrong about what's actually happening. Because gravity, as we describe it, isn't a force whatsoever. And once you truly see what gravity really is, the entire universe rearranges itself in your mind. Let me show you. Stand up right now. Feel that pressure in your feet. What is that sensation? You'll say, gravity pulling me down. But focus on what you actually feel. The floor pressing upward into you, pushing. That's the physical sensation. The upward shove. The mysterious downward pull we talk about, you never feel that. Not once. You feel only the push. Always up, never down. So where is this alleged pull? Here's something even stranger. The moon is currently falling toward Earth. Has been for billions of years. Yet it never lands. It just keeps looping around. Endlessly falling, but never arriving. What kind of pull behaves like that? Pulling forever, but never closing the gap. And Newton said this pull acts instantly. Move Earth, and the moon supposedly knows right away. Across hundreds of thousands of miles with no signal, no mechanism. Newton himself admitted he had no clue how this worked. Action at a distance, he called it. Even he found it unsettling. But the equations fit so beautifully that everyone let the discomfort slide. They shouldn't have. Go back in time. People didn't know why planets wandered the sky the way they did. Copernicus said they orbit the sun. Fine. But how do they move? What paths do they trace? Tycho Brahe built a pre-telescope super observatory and documented planet positions for decades. Meticulous, relentless measurements. Why that level of precision? Because reality does not yield its secrets to guesses, only to careful, disciplined observation. His mountain of data was inherited by Johannes Kepler. Kepler wanted the shape of planetary orbits. He tried perfect circles, close, but Mars was off by 8 arc minutes, an error most would ignore. But Kepler trusted Tycho's accuracy. He knew 8 arc minutes wasn't a mistake. So he scrapped his idea and rebuilt from nothing. Years of work later, he found the answer: ellipses. Orbits are ellipses with the sun at one focus. A perfect match, elegant, a triumph. But it raised a bigger question: why ellipses? Meanwhile, Galileo rolled balls down ramps. Simple? Not really. Roll one down a slope, it speeds up. Let it go onto a level surface, it keeps moving. Doesn't stop immediately. Remove all friction and it would glide forever. This contradicted centuries of intuition. People believed constant motion required constant push. Galileo showed the opposite. Motion is natural. Change in motion needs explanation. Slowing down, that's friction. Speeding up, that's a push. Bending a path, a sideways force. That's inertia, the first law of motion, which led to a puzzle. Planets should move straight forever. That's inertial motion. But their paths bend around the sun. Something must continually nudge them sideways. What? Newton saw the answer. Planets want to go straight, but their trajectories curve. Something redirects them at every moment. He labeled it gravity, a universal attraction between masses. Depends on mass and distance. Stronger when closer, weaker when farther. Falls off with the square of distance. From that one idea, everything clicked. Ellipses, Kepler's laws, orbits. Planets are falling toward the sun while moving sideways, creating elliptical tracks. The moon orbits Earth by constantly falling but always missing. Apples drop because Earth pulls them. Newton famously compared how far the moon falls each second to how far objects fall near Earth's surface. The numbers matched. Same law governing apples and the heavens. Unification. Stunning. Tides. Earth's equatorial bulge. Cometary returns. Light delay measurements. Predictions of Neptune. Orbital perturbations. Newton's law explained it all. But one detail remained mysterious. Drop a feather and a hammer in a vacuum. They hit together, perfectly synchronized. But the hammer has more mass. Newton's rules say gravity grabs it harder, much harder. But its inertia also increases proportionally. Those effects cancel exactly, always, for all materials. Why should gravitational mass and inertial mass be identically proportional? Newton had no explanation. A cosmic coincidence, he thought. Or was it? Einstein asked, what if that equality is a clue? A signpost? Imagine you're locked inside a windowless room. You feel your weight. Are you standing on Earth or in a rocket accelerating upward at 9.8 meters S2? There is no experiment, none at all, that lets you distinguish the two. Drop something, it plummets to the floor in both cases. Toss a ball, it curves the same way. Stand on a scale, the reading G is identical. No difference. This is the equivalence principle. Gravitational effects and acceleration are indistinguishable. If you can't tell gravity from acceleration, maybe they're the same thing. Here's Einstein's radical insight. An object in free fall experiences no force. The apple dropping, the moon orbiting, satellites circling Earth, astronauts drifting weightlessly, none of them feel any force at all. They're following natural paths, straightest paths, no pull, no mysterious interaction. But the apple is falling. Isn't that acceleration? What if it isn't? What if the apple is moving straight through a curved scaffold of space and time? This is Einstein's revolution. Gravity isn't a force between masses. Gravity is the bending of space-time. Massive objects reshape the geometry around them. They deform it. And objects simply follow the straightest possible lines within that geometry. The apple isn't yanked downward. It is traveling straight through curved space-time, and straight just happens to point toward Earth's center. You standing on the ground aren't pulled down. You're being pushed up by the floor, prevented from following your natural free-fall trajectory. That upward push is what you feel as weight. You are constantly being forced away from your natural path. Einstein made a testable prediction. If gravity is curvature, light must bend. Light has no mass, but if space is curved, light must follow the curves. During a solar eclipse, starlight passing near the sun shifted just as Einstein predicted. Gravitational lensing, now we see it everywhere. Galaxies, warping the images of galaxies behind them. Direct proof, space itself is curved. People say, why astronauts are weightless? Because there's no gravity in orbit. Wrong. At low Earth orbit, gravity is almost the same as here, about 90%. They float because they're falling. The spacecraft falls. Everything inside falls, all together at the same rate. No relative forces, so it feels like floating in deep space. Free fall equals weightlessness. Gravity and acceleration blurred into one phenomenon. Think of Earth's surface. It's curved yet seems flat locally. That's the trick of geometry. Why is Earth round? Gravity. But not because a force pulls everything inward like a rubber band. Instead, because space-time curves evenly in all directions. Matter tries to follow the geometry, and the stable configuration that emerges is a sphere. And the curvature isn't just in space, it's in space-time. The sun carves a deep well, Earth a smaller one. You carve a tiny dent. Objects move in these contours, not force simply following the shape of reality. The moon's orbit is the straightest path in Earth's curved space-time. Apples drop because time flows differently near Earth. The parabolic arc of a thrown ball isn't a result of a pull. It's the natural line in a warped geometry. When you stand still on Earth, Newton would say two forces balance, gravity down, ground up. Einstein says only the ground pushes, and because the ground pushes, you accelerate upward relative to free fall. You are just like someone in a rocket accelerating upward. Weight isn't a downward force. It's the upward shove that stops you from moving naturally. When a branch supports an apple, it's pushing the apple upward. When the branch snaps, the push stops. The apple is released to follow its natural path through curved space-time. It falls because it finally moves straight. Now consider extreme cases. A star's mass creates a deep space-time valley. Nuclear pressure keeps it from collapsing. When its fuel runs out, that support disappears. Collapse begins. If the star is massive enough, even nuclear resistance fails. Matter compresses to neutron star densities, a teaspoon weighing billions of tons. Go higher in mass and even neutron pressure fails. Space-time warps so intensely that every path curves inward. Light cannot escape. A black hole forms. We don't see black holes directly. We see the chaos around them. Matter spiraling inward, heating, glowing, before vanishing beyond the event horizon. All because mass sculpts space-time. One idea, mass curves space-time, explains planetary orbits, tides, Mercury's orbital precession, gravitational lensing, black holes, gravitational waves, from planetary motions to the grand architecture of cosmic structure, the same principle reigns. Newton's equations work beautifully for most tasks, launching rockets, planning missions, but Einstein tells us what gravity is. Mass shapes spacetime. Spacetime shapes motion. When you step on a scale, you're not measuring a downward force. You're measuring the upward push needed to keep you from free falling. When something drops, you're watching an object freed from constraint, finally following the contours carved by mass. When you look at the moon, you're watching an object moving straight through a curved universe. Gravity isn't a pull, it's geometry. And that is far more astonishing than any invisible force could ever be